Welcome all of you to the tutorial video lecture on linear momentum analysis. In this tutorial video lecture, 4 different problems will be discussed. So let us start with the first problem. This tutorial video lecture corresponds to the topic 5. So we'll start with example problem 5.1. I welcome all of you to the tutorial video lecture on linear momentum analysis. This topic, linear momentum analysis, corresponds to topic 5. So let us start with example problem 5.1. This problem corresponds to force due to a jet impinging on a stationary or moving vane. So we'll consider 2 cases. What is vane? Vane is a blade which is fitted to a wheel which is free to move. So if you have a vane on which there is a, let us say, a water jet or an air jet is hitting on a vane, then we'll consider 2 cases: if it is stationary or if it is moving. What is the force that is exerted by the jet on the stationary or moving vane? So this is a vane which is like a blade which is fitted on a wheel which is free to move, and this is a jet. Let us say it's a water jet which is striking on this vane, and you can see that it sticks to the surface of the vane and it moves with a constant velocity. We are assuming that the velocity of the jet remains constant as it passes over the surface of the vane. However, you can see that the magnitude remains same. The magnitude of this velocity remains same, but there is a change in the direction. The entry is horizontal while the exit is inclined. And the inclination angle is represented here by, as shown here, theta. Horizontal direction is the x direction, vertical direction is the y direction. So basically, we are in this problem, we do a control volume analysis where we take a control volume, we choose a control volume such that the control volume is passing normally through the inlet and outlet. So you can see that for a horizontal inlet, the control volume that we have taken here is a vertical, whereas for the inclined exit, the surface of the control volume is inclined at this portion. So, if I show you this control volume separately, to represent the external forces acting on this control volume, we are interested in this problem to determine the force that is exerted on the vane, or to calculate the force that is exerted on the vane. First, we'll calculate the force that is required that acts on the control volume. So here, the external forces, the control volume is shown separately, and the external forces that are acting on this control volume is shown here. Now, the arrows which are shown here corresponds to the pressure. Note that the jet is moving in an atmospheric condition, and there is no change in the pressure as it is moving in the atmosphere. So everywhere pressure is atmosphere. So on this control volume, if you represent the pressure everywhere is same, that is atmospheric pressure. Other than the atmospheric pressure, the external force that acts on this control volume is the weight. Note that this weight corresponds to the weight of the water inside this control volume as well as the weight of the vane. Other than this, we have certain reaction forces which are acting on the which are the forces which are acting on the control volume. These forces are acting on the control volume, which are reaction forces, which keeps the vane stationary. However, if you consider the surface of the vane, on this vane, when the jet hits the vane, there is an active force. Now, to keep the control volume, you have a reaction force. These are the reaction forces. But if you consider the force which is acting on the surface of the vane, it is in the, if it is in the positive direction, this is in the negative, this Fy is in the positive direction. So on the vane, it is in the opposite direction. So you can see Fx is horizontally left to right on the control volume, but on the vane it is in the opposite direction. So note that the forces that are acting on the control volume, these are reactive forces, and the force that is acting on the vane is of equal magnitude but in opposite direction. In this problem, you are given the jet velocity, which is this. You are given the diameter of the jet, and you are given the inclination angle, which is the corresponding to the inclination at the exit of this wave. And you have to determine the forces that are acting on the stationary and moving wave. So these are the two cases that we have to solve. Case A, where vane is stationary. So this is the velocity of the wave, uv is equals to 0. Whereas in case B, this is non-zero. So for these two cases, we are interested to determine the force that is required, that is acting on the vane. So let's take a first case, stationary vane. Now here we are assuming that the flow is stationary. We are also assuming out of the various external forces, you can see the net pressure force is 0 because all over the control volume, same pressure force is acting. We are neglecting the weight of, in this problem, you are not given any data about the weight. So we are neglecting the weight of the water as well as the weight of the vane inside this control volume. So the external force is only the reaction forces, this Fx and Fy that is acting. We are assuming that the flow, the jet that is passing through this control volume, it has reached to a steady state. So if you take a steady state case and if we express the equation for momentum conservation, the integral equation in my lectures, video lecture, I had shown you that the integral equation for momentum conservation on the right hand side, which consists of surface integral, it can be converted into an algebraic equation where the net external force is equals to the net momentum flow rate leaving across the surface of the control volume. So if you want to calculate net momentum flow rate leaving the surface of the control volume, this is the momentum flow rate that is leaving and this is the momentum flow rate that is entering. Note that this velocity u vector has two components, the horizontal component u and the vertical component v. So in a 2D, this is ui plus vj. So this equation represents the net force acting on the control volume, which is this force, is equals to net momentum leaving the control volume minus this is the momentum flow rate leaving the control volume, this is the momentum flow rate entering the control volume. If you want to calculate the, whenever we apply the force, this is a vector equation, we have always applied component by component. So if you want to apply in the x direction, to calculate Fx, note that this velocity vector, we have to use the x component because this m which is shown here is the mass flow rate. Mass flow rate multiplied by the velocity, which is a vector, is called here as momentum flow rate. Now, if this vector, if we use the scalar component u, then this will become x momentum flow rate. So note that here this equation shows the force which is acting in the x direction is equals to the net x momentum flow rate leaving across the surface of the control volume. To calculate the net x momentum flow rate leaving, this is the x momentum flow rate leaving from the outlet minus entering from the inlet. Now this is to calculate the net, the reaction force acting on the control volume in the y direction. This is equal to the y momentum flow rate. This is the, now note that this is the y momentum flow rate. This is the y momentum flow rate, where this is the product of mass flow rate into v velocity. Note that when you have a product of mass into the horizontal velocity is a momentum. Here, this is not a mass, this is mass flow rate. So here we are having mass flow rate into the horizontal velocity. This we are calling as x momentum flow rate. When you have mass, product of mass flow rate with vertical velocity, we are calling it as a y momentum flow rate. So the net force acting in the x direction is equals to x momentum flow rate leaving from the outlet minus x x momentum flow rate entering. And the net force, the reaction force in the y direction on the control volume is equal to y momentum flow rate leaving minus y momentum flow rate entering. Now, you can see that to calculate Fx, this is the horizontal velocity. Now, the horizontal velocity at the outlet is uj cos theta. So this the horizontal velocity at the outlet is uj cos theta. The horizontal velocity at the inlet is uj. So this is shown here. This horizontal velocity outlet is uj cos theta, and the horizontal velocity at inlet is uj, which is the jet velocity. If you see the vertical velocity, what is the vertical velocity at the outlet and inlet? And the vertical velocity at the outlet is uj sin theta, whereas the vertical velocity at the inlet is 0, which is as shown. So with this, I have shown you, we started with a vector form of the equations where we have represented force as a vector, and we have represented momentum flow rate where we have taken the velocity as vector quantity. Any vector law or any vector equation, you always apply component by component. So I had shown you now its application in the x and y direction. Now in the x direction, basically we do a bookkeeping where we keep account of the momentum flow rate. Momentum flow rate that is leaving, we take it positive. Momentum flow rate. So for Fx, we have x momentum flow rate. So for Fx, we have accounted. We are doing a bookkeeping of x momentum flow rate entering and leaving. So whichever is leaving, we keep it with a positive sign, and the x momentum flow rate entering, we take it with a negative sign. Similarly for y, instead of x momentum flow rate, now we have a y momentum flow rate. Here I had shown you the velocity, but this mass flow rate, note that you have one inlet and one exit, and you have a steady flow situation. So whatever mass flow rate is entering by mass conservation, that was the previous topic. By mass conservation for a steady flow, whatever mass flow rate is entering, that has to leave from here. So MO is equal to MI, let us call it M, and this is equal to density into area into the velocity of the jet, which is uj. This is the density, this is the cross-sectional area of the jet. Now, if you know the diameter of the jet is a circular jet. This is given to you. So you can take it as pi by 4 dj square. And this is the jet velocity, which is given by here as uj. So this gives you the mass flow rate. So once you know this mass flow rate and all these velocities, the horizontal velocities at the outlet and inlet, the vertical velocities at the outlet and inlet, you substitute this mass flow rate and these velocities, and finally you obtain an expression for the reactive force acting on the control volume as mass flow rate into uj cos theta minus 1, and the reaction force acting in the y direction is 2. So this mass flow rate you can take common, this will become uj sin theta. Here it is m uj cos theta minus m uj. So when you take m uj common, it is cos theta minus 1. These are the reaction forces which are acting on the control volume. Now the actual force that is acting on the vane is corresponds to the negative sign of these forces. Now let us take a second case. If the vane is moving with velocity uv, so in this case, when the vane is moving with velocity uv, then as shown here, so this vane is moving with the velocity uv. So then we take a control volume, which is a moving control volume. The control volume moving with a constant velocity. Note that in this topic, we consider a situation which we call as the inertial control volume, where it can be stationary or it can be moving at a constant velocity. We are not considering a problem of an accelerated control volume or a non-inertial frame of reference. So when this vane is moving with a constant velocity uv, we take a control volume which is moving with the velocity of the vane. So if we have a moving control volume. Now, the moving control volume, when we consider the velocities which are entering or leaving the surface of the control volume, we have to use a relative velocity. Now to calculate the relative velocity, we have two velocities. One velocity appears while we are calculating the mass flow rate, and another velocity appears when you want to calculate the x momentum flow rate and y momentum flow rate. The velocity that appears for calculating fx is the x momentum flow rate, and in the x momentum flow rate, along with the mass flow rate, the velocity is u velocity. Whereas for when we want to calculate fy to calculate y momentum flow rate, then the vertical velocity v appears. However, note that in the mass flow rate, you have a normal velocity. Now, the mass flow rate earlier I had shown you rho aj into uj, but now in this case, the jet is entering with this velocity uj, but the vane is moving with the velocity uv. So when we consider the relative velocity with which the jet is entering inside this control volume, this will be uj minus uv. So here we consider the relative velocity to calculate the mass flow rate. Now when we want to calculate the force acting on the control volume in the x direction, note that we are considering the mass flow rate that has been obtained using the relative velocity. And then to calculate mass flow rate, we consider basically this m now has become mr, where mr means it is using a relative velocity. Now we can follow the same procedure that I had shown earlier for a stationary wave, but this is the expression that we have obtained for note that these are the forces which are acting on the control volume. These are the reactive forces. Now this m has become mr, but now this uj jet velocity will be also a relative velocity. So this uj now will become uj minus uv, which is the vane velocity. And so we are using the same expression, that is, I'm just drawing an analogy. These are the expression that we obtained from stationary wave, but when we want to use it for a moving wave, this velocities will be relative velocities. So you get uj minus uv. Note that the relative velocity appears in this term as well as in the mass flow rate. So this mass flow rate also has a relative velocity. And then we will have for fx, as we had earlier, here we will have cos theta minus 1. For fy, now you can understand that for fy, for moving wave, this will be mr uj minus uv sin theta, as shown. So with this, we have obtained the forces that are acting on the control volume, and as I had mentioned, these are reactive forces. Our objective is to obtain the active forces which acts on the vane, which is acted by the jet when it changes its direction while moving on the vane. Now the active forces, so the active forces which I had shown here, which are acting on the vane, are of same magnitude but in opposite direction. So these are the active forces acting on the vane. Till now we have obtained the reactive forces. So the active forces are basically, the relationship is a negative sign between the two. So this fx is equals to minus of fx vane. Fy is equals to minus fy vane. So the fx vane, now instead of cos theta minus 1, you will have 1 minus cos theta. Okay, so you can see here it is fx is cos theta minus 1, but you calculate when you obtain the active forces which is acting on the vane, you get 1 minus cos theta. Once we obtain the force acting on the vane, we want to calculate the power, because if this vane is, as I said, it's a blade which is fixed on a wheel, and the wheel is free to move. So if the wheel is free to move, then you can generate a power. So the power generated is given by the force multiplied by the velocity of the vane. So if you take the product of this, the velocity, you obtain an expression which is shown here. This is the power that is generated. Now, if you see this, so if you plot a curve between power, So in the y-axis, I have shown you power, and in the x-axis is the vane velocity. Now this power is 0 when the jet velocity is equals to vane velocity, and it is also 0 when the vane velocity is 0. Okay, so when uv is 0, that's the first case. The second case is ug is equals to uv, which means jet velocity is equals to vane velocity, then the power generated is 0. However, if you plot this expression for different uv, you get an expression like this. For different uj and uv, you get an expression, you get a curve like this, where there is a maximum. Now we are interested to know this maxima occurs at under what condition. So basically in this expression, if you take the derivative, this expression, let us suppose we have a fixed jet velocity. So if you calculate dp by duv, so the maxima corresponds to a condition. So this is corresponding to the 0 condition where uj is equals to uv. Uj is equals to uv. Now for the maxima, you take the derivative of in this expression, dp by duv is equals to 0 as shown here. So here you have a basically uv, and here you have a uv square. So you have uv2, and when you take this derivative, you get a second, you get a quadratic equation which has 2 roots, and one of the root comes out to be uv is equals to uj by 3. So this indicates that this maximum power is generated when the vane velocity is 1/3 of the jet velocity. This is applied in turbine which is called as Pelton wheel to generate the power. Example, so from the next problem that is considered here is as example 5.2. Here we calculate the force to hold a deflector elbow in place. What is a deflector? The deflector, basically, if you consider the flow in a pipe, to deflect, or it is deflecting at an angle theta, I will show you a deflector. So this is, let us suppose, a horizontal pipe, and this is an attachment which basically deflects the horizontal flow to some an angle which is theta. And note that the cross section of this deflector is reducing. So it is also, it's not only deflecting, but it is also accelerating. So the velocity at the inlet is u1, and at the outlet the velocity is u2, and the cross section is reducing, the velocity is increasing. Now this is the control volume that we consider. Here also you can note we choose a control volume such that at the inlet and outlet the control volume, surface of the control volume is normal. If you consider the external forces acting on the surface of the control volume, these are the pressure forces which are acting, these are the external, and all these pressure forces are atmospheric except at the inlet. Note that whenever you consider a fluid coming out in the atmosphere, note that here fluid is going in. Okay, so it may be coming from a pump, water, you may be using a pump to push the water upward. So here the pressure is more, whereas whenever the water comes out, it comes out in the atmospheric pressure. So at the outlet, you always have atmospheric pressure, and this surface of the control volume, all these are subjected to atmospheric pressure, and at the inlet, you have a larger pressure. So that's why you can see here at inlet, you have a larger pressure. So if you consider the pressure everywhere, it's atmospheric. At the inlet, you have a larger pressure. Other than this, the external forces acting on the control volume is the weight of the water as well as this deflector along with the support. So you have external forces as weight, pressure, and then you have a certain reaction forces which are acting on the control volume. Note that these are the reaction forces which are, for all the problems, note that I'm considering the reaction forces in the positive x and positive y direction. If the magnitude comes with a negative sign, then then there is a change in the direction of the reaction forces. This we are considering as inlet, which is the inlet of the pipe, and the deflector outlet. This is considered as section 2. You are given for this problem the mass flow rate at the inlet, which is shown here. The cross-sectional area at the inlet. This A1 is the cross-sectional area at the inlet. A2 is the cross-sectional area at the outlet. this Z is the difference in the elevation between the inlet and the outlet. So this is the center line of the uh, deflector, the center line of the pipe, and this is the this is the exit of the deflector. So the difference in the elevation between the inlet and the outlet of the control volume is Z. This difference in the elevation is also given to you. Note that in this case, although you are given an inlet mass flow rate, but the flow is considered steady here, and although the cross-sectional area is changing, but for a steady flow, if you apply mass conservation, the M1 is equals to M2, and you are given A1, A2. So once you know the mass flow rate A1, A2, you can calculate the velocity at the inlet, this U1 and U2. The weight for this problem, we will consider negligible, and you have to determine the Fx and Fy for this problem. Now the solution, we first start for that with a condition that for a steady flow, M1 is equals to M2 is equals to M, and we calculate the velocities, and using those velocities we'll calculate the x momentum flow rate and y momentum flow rate to finally calculate the Fx and Fy that we have to determine for this problem. So note that I am showing you the velocities at this I is the inlet, this O is the outlet, and using this velocities as well as the mass flow rates, which is M, we will obtain the x momentum flow rate at the inlet outlet, y momentum flow rate at the inlet and outlet. So this is the, so you can obtain this U1 as I mentioned earlier as mass flow rate, A1, so you take the ratio, then you can calculate the, sorry I missed here, there should also be density which is missing. Let me write it down. Okay, so the velocity is equals to the mass flow rate divided by the density into A1, and density for U2 it will be density into A2. Now, if you want to calculate the x momentum flow rate, I had mentioned x momentum flow rate is equals to mass flow rate into the velocity. Now the horizontal velocity at the inlet is U1. Horizontal velocity at outlet is U2 cos theta. So this is the x momentum flow rate at the inlet, and this is the x momentum flow rate at the outlet. Similarly, the vertical velocity that will come when we calculate the y momentum flow rate. Y momentum flow rate is this y momentum flow rate is the product of mass flow rate into v velocity, which is a vertical velocity. Now we have to see what is the vertical velocity at the inlet and outlet. Vertical velocity at the outlet is u2 sine theta. Vertical velocity at the inlet is 0. So the y momentum flow rate at the inlet and outlet, inlet it is 0, outlet it is consisting of u2 sine theta as shown here. So using this x momentum flow rate and y momentum flow rate, we can obtain the now this using this this is used to calculate the reaction force in the x direction. So the next net external force in the x direction is, note that you don't only have Fx here, but this pressure, if you basically on the other at the outlet you have an atmospheric pressure. Everywhere you have an atmospheric pressure, and as I had mentioned in my lecture videos, that whenever you have on the control surface everywhere atmospheric pressure and at some portion you have a larger pressure, then we work with gauge pressure. So the external force not only consists of this Fx, but it also consists of the gauge pressure P1 gauge multiplied by A1. And note that this is also acting in the positive x direction, so it is the net external force in the positive x direction is Fx plus P1 gauge into A1. Now this will be equal to the net x momentum flow rate leaving, which is this, minus the net x momentum flow rate entering. Okay. Now this Fy will be y momentum flow rate leaving minus y momentum flow rate entering. So using this, you get an expression for Fx as this, and for Fy you get an expression like this. Note that Fx consists of the mass flow rate, the x momentum flow rate, where the velocities here are the horizontal velocities, whereas in Fy you have a vertical velocity which is a v velocity. Now, to calculate this fx, fy, you know all this mass flow rates and the velocities, but what you don't know is this P1 gauge. So the next object we will determine this. What is this pressure, gauge pressure at the inlet? Now, to calculate the gauge pressure in inlet, we apply the Bernoulli's equation that was presented in the previous topic on mass conservation in Bernoulli's equation. So we'll apply the Bernoulli's equation between 1 and 2, which is our inlet and outlet. And you can see that there is a difference in the elevation between 1 and 2, which will give rise to, which will let us determine the gauge pressure. Also, we have a difference in the velocities. So note that this Bernoulli's equation, there are Bernoulli's equation of 3 different forms. Here, the Bernoulli equation that is presented is in the pressure form because we are interested to determine the gauge pressure. So P1 plus rho 1 U1 square by 2 plus rho g Z1 is equals to, at the outlet given atmospheric pressure. So P2, instead of P2, I am writing P atmospheric plus rho U2 square by 2 plus rho g Z2. Now, from this, you can obtain the gauge pressure P1 minus P atmospheric is equals to rho U2 minus U2 square minus U1 square by 2 plus rho g Z2 minus Z1. This Z2 minus Z1 is the Z which is shown here, which is given here. And this U1, U2 you have already determined from the mass flow rate and the cross-sectional area and the density. And so this is the gauge pressure that you were interested to determine to finally calculate the fx. So from this expression you can obtain the gauge pressure, and using the gauge pressure you can calculate this fx. Okay, so with this I had shown you 2 problems where in the first problem it was the force acting on the vane by a jet. In the second problem it was the force to hold the deflector. I would like to highlight here before I go into the next problem that the previous problem that I had presented, which is as shown here, this problem is an external flow problem. Okay, here the jet is under atmospheric condition and the jet velocities at the inlet and outlet both are, because every jet is in the atmosphere, so its pressure is uniform everywhere, it is atmospheric. But in the second problem is an internal flow problem where it is flowing inside a deflector. However, it so turns out it is this water is exiting at the atmosphere, so that's why you have an atmospheric pressure at the outlet. But then at the inlet you have a larger pressure. This is an internal flow problem where in certain problems for an internal flow, if you need to calculate the pressure, note that you have to use the Bernoulli's equation. I'm just highlighting why Bernoulli's equation was not needed in the previous problem and why this is needed for this problem. So keep this in mind while solving the problem. So after these 2 problems, let us go to the third problem. The third problem corresponds to an external flow problem. The problem is basically we use a method commonly in experiment which is called as wake survey method to calculate the force exerted on a solid body in a free stream flow. This solid body could be like a flow across an aeroplane or flow across a car. But for simplicity, let us take flow across an object which is of circular shape. Let us suppose this is a circular shaped object and the fluid is entering from the left region of, this is the control volume that we are considering. This is the fluid which is entering, and let us suppose in an experiment, you do an experiment and you are able to determine, this is the center line of the control volume, and above the center line the length is L and below. So we'll define X and Y. This is the diameter of the circular cylinder and these are your X and Y directions. So let us suppose you do an experiment, and by doing the experiment, let us suppose you obtained the velocity profile as shown here. I would like to point out that the maximum velocity, which is at the top of this vertical line, top as well as bottom, is fact the velocity distribution is symmetric about the center line, and the maximum velocity is at the tip, at the end of this vertical line, u infinity at the top as well as bottom. And the velocity is gradually reducing as you move towards the center in this velocity profile. This u velocity profile, this horizontal velocity profile, u is varying with respect to y. Okay, so note that here you are given a constant velocity, here you are given a velocity profile. Note that as compared to the previous problem, in the previous problem you were given single value of the velocity at the inlet and outlet. Whereas in this problem, you are given a velocity profile. So to calculate the mass flow rate as well as momentum flow rate, note that we don't use an algebraic equation, we use an integral form of equations. I had mentioned in my lecture videos that for most of the problem, when you are given a single velocity, single valued velocities, then you can use algebraic form of the equations. But at certain boundaries of the control volume, if you are given velocity profile, then make sure to use the integral form to calculate the mass flow rate and momentum flow rate. In integral form, for at this point, mass flow rate is integral of rho u as a function of u as a function of y dy. Okay, so basically we do a integral with respect to, in this case we are considering the surface area, we are considering this is a 2D problem where the dimension perpendicular to this plane is, we are taking as unity. So the mass flow rate is basically given by, mass flow rate is strictly speaking integral of rho u ds, but this surface area we are considering in the 2D, the surface area becomes a line, and then we are taking mass flow rate for this will be integral of rho u dy. Whereas if you calculate the momentum flow rate, x momentum flow rate, now x momentum flow rate involves velocity in the x direction, which is again uy. So then it becomes integral of x momentum flow rate at this boundary will be integral of rho u square dy. Whereas the mass flow rate, if you want to calculate here, you have a uniform velocity. So you can use an algebraic type of equations where the mass flow rate will be like rho into area. In this case, you can take it to be 2L into 1, and density into area into velocity will be u infinity. So in this case, the mass flow rate will be rho 2 rho L into u infinity, and the momentum flow rate will be 2 rho L. Mass flow rate you have to multiply by the horizontal velocity, which is again u infinity. So the x momentum flow rate at the inlet will be 2 rho L u infinity square. Another important thing you can note from this is that although you are given the velocity profile at the left boundary and the right boundary of the control volume, you also need to realize, in fact that is the key to the solving this problem, is that what do you expect? All the mass which is entering from the left boundary, whether it is leaving from the right boundary or not. If you can see, basically to calculate the mass flow rate, basically you have to do an integral. So basically you have to obtain the area under this integral. Now area under this integral, you can see it is larger as compared to the area under this integral. You have u infinity only at the ends, whereas you have u infinity uniform everywhere on the complete height. The height of the left boundary and right boundary is same. Okay, so near the center, basically there is a velocity deficit. So you have a low velocity towards the center. So there is a less mass flow rate. If you calculate integral of rho u dy here and integral of rho u dy here, you can see from here that it is expected that in this case the mass flow rate is less. So more mass is coming inside this control volume and some is leaving from here. Where is the rest of the mass going? We are assuming that the flow is steady in this problem. So the mass cannot be generated or destroyed. It has to leave. So it has to basically leave from the top surface and the bottom surface. So note that there is a mass flow rate, not only from the mass flow rate is entering from the left wall, but it is not only leaving from the right wall, but it's also leaving from the top and the bottom wall, which I'll call as side walls. And note that on the side walls, top and bottom walls, you have a velocity which is u infinity. So note that to calculate x momentum flow rate, first we'll calculate the mass flow rate on the side walls and we'll multiply by this horizontal velocity to calculate the x momentum flow rate leaving from the side walls. While solving by momentum analysis, for many a problem, we have to use mass conservation. Okay, so while solving momentum conservation, whenever you take a control volume, first make sure that mass conservation is obeyed. If you don't do that, you may do mistake and you will solve this problem wrongly. You can miss that the X momentum flow rate is living from the side walls also, which is in fact, this is the key to the solution for this problem. This is the reaction force acting on the control volume. Note that here we are interested not in the reaction force, we are interested in the active force which is exerted on the solid body. So first we'll calculate this Fx, but then we'll take its negative sign to obtain the active force that is exerted by the flow of by this fluid flowing over the circular body. That active force we call it as a drag force. Like if you stand in a river and if the fluid is moving from the left side, the water in the river basically tries to push you along its direction. Okay, so that is the active force. Okay, so we are interested in calculating that active force. Although the reactive force I am presenting as this, but actually this will come out to be a negative value, and if you take a negative or negative, it will become positive. So the active force, the drag force, we'll calculate. So first we'll calculate the reactive force, and then we'll take its negative sign. So we derive. So in this problem, you need to derive a non-dimensional form of the force acting along the flow direction. This is called as drag force. This is the force acting on the cylinder. We non-dimensionalize it for a 2D problem by half rho u infinity square d, where u infinity is the free stream velocity at the inlet and d is the diameter of the cylinder. So first let us calculate this Fx, then we'll calculate Fx cylinder equals to minus of Fx, and then we'll divide this half rho infinity is d, and then we want to derive this expression. Where these velocities are u star, everything with a superscript star. When we have star, this is called as non-dimensional. So in fluid mechanics, in the next topic, I will teach about non-dimensionalization. It's a very powerful concept. So this expression is a non-dimensional expression. Note that if you take the unit of rho u infinity square d, its unit come out to be 4. So when you divide a 4 by another 4, this is a non-dimensional representation. So this is a non-dimensional representation of the force acting along the flow direction. This is called as non-dimensional drag force, which is called as drag coefficient. This is expressed in terms of the integral in terms of the non-dimensional horizontal velocity, non-dimensional y-coordinate, and L star, where L is the half of the height of the dome. Here you can note this u star is given as the ratio of u divided by infinity, y star is y divided by the diameter of the cylinder, L star is L divided by. Whenever you solve a fluid mechanics problem, there is a certain at least one value of velocity and length scale which is given to you, which we use as a non-dimensionalizing length scale. In this problem, u infinity is given to you, so that we use to non-dimensionalize the velocity. As far as length is concerned, you are given the diameter of the cylinder, so that we use to non-dimensionalize the coordinates. Okay, so why we are non-dimensionalized by d. This length also, half of the length of the domain, we are non-dimensionalized by the diameter of the cylinder. So first let us obtain the reactive force acting on the control volume. Now to do that, we are interested in force only in the x direction, not in the y direction. So we'll calculate these x forces. Basically, here we are interested in x momentum flow rate. So in all this, I'll call this as left wall, this I'll call it right wall. The top and bottom together I'll call as side wall. So basically, we are interested in calculating the x momentum flow rate for the different walls. This is the general expression to calculate the force, reactive force acting in the x direction on the control volume. This is equals to the x momentum flow rate leaving the control volume minus x momentum flow rate entering into the control volume. Okay. I'll again repeat, mass into u velocity is momentum. Here we have this m is not mass, this is mass flow rate. So when you have mass flow rate into u velocity, this is the momentum flow rate. This is the momentum flow rate at the outlet minus momentum flow rate at the inlet. Note that in this case, I had mentioned earlier, there are two outlets. Fluid is not only leaving from the right wall, it is also leaving from the top and bottom wall. And so there is one inlet and If you want to say, you can have say 3 inlet: top wall, bottom wall, and right wall. But I will classify only as 2 outlet. One is this right wall, and another I'll call as side walls. So at the inlet, let us first calculate the mass flow rate. At the inlet on the left wall, which is this, the mass flow rate I had mentioned, this is equal to your velocity. Basically, we calculate integral of rho u dy. Now this u is u infinity, which is a constant. So basically, you get rho u infinity integral of dy minus L to plus L, which is 2L. So you get 2 rho L u infinity as the mass flow rate at the inlet. If you want to calculate the mass flow rate at the outlet, there are 2 outlets I had mentioned. One outlet is this right wall, where you can calculate the mass flow rate as rho density. Actually, initially we take it inside the integral, but in this case we are considering the fluid as incompressible. So it's a constant, we take it outside the integral. So the integral of minus, so if you want to calculate the mass flow rate, this velocity profile, you have to integrate from minus L to plus L. And these are the L's, and this is your XY coordinate system. So rho integral of minus L to plus L u y dy. So with this we calculate the mass flow rate. Instead of minus L to plus L, we can write it as an integral from 0 to L. So we can express this as 2 rho integral of 0 to L u dy. Now, as I mentioned earlier, that in this case, we need to realize, which is very important for this problem, that although you are given velocity profiles only at the inlet and outlet, but at the outlet mass flow rate is less than the inlet mass flow rate. So you also need to realize, which is like hidden in this problem, that there is another outlet, which I am calling it the side outlet, corresponding to top and bottom wall. And the mass flow rate, if you apply mass conservation, under steady state flow, whatever mass is entering, that mass has to leave. So ML is equal to MR plus MS. So MS will be ML minus MR. Mass flow rate on the left wall minus right wall will be the mass flow rate on the side wall. So you basically subtract this, which is 2 rho L u infinity minus 2 rho integral of 0 to L u dy. Okay, so this is the mass flow rate which is leaving the top and bottom surface, which I call as side surface of the control volume. I am putting both mass flow rate together as MS is a single term. So with this, I had shown you the mass flow rate. Now to calculate the momentum flow rate, we have to multiply it by the velocity in the x direction. Okay, so the mass flow rate. So now, as far as the velocity in the horizontal direction is concerned, for the left wall you have u infinity. For the top and bottom side wall, so you can multiply this to calculate x momentum flow rate from the left wall. You have to just multiply by u infinity. So this will be 2 rho L u infinity square. For the side wall also, the horizontal velocity at the side wall is u infinity. So you take this this momentum flow rate from the side wall, and you multiply by u infinity. Whereas to calculate momentum flow rate from the right wall, note that on the other walls you are given a constant velocity, but on the right wall you are given a value of the velocity. So as I had mentioned in the beginning of this problem, wherever at certain boundary, if you are given a velocity profile, to calculate the mass flow rate as well as momentum flow rate, you have to write an integral equation instead of algebraic equation. Okay, note that these algebraic equations are used for those problems where you are given single valued of velocities at the boundary of the control surface of the control volume. Okay, so for this surface, we will use an integral equation, and we know that integral equation. That integral equation is basically integral of minus L to plus L rho u. Now, to calculate mass flow rate, we take the normal velocity. This u is the horizontal velocity, which is appearing because of this, whereas this velocity is corresponding to the mass flow rate. Now, it so happens that the velocity, and if you see the velocity which is in horizontal direction, if you draw the normal of this vertical place, it is also in the horizontal direction. So this u dot n is also a velocity in the horizontal direction. So this will become rho u square dy. Okay, although right now it is minus L to plus L, minus L to plus L rho u square dy, but later on we'll convert into, we write it as twice of integral of 0 to L rho u square dy. So this is the momentum flow rate leaving from the right wall. Okay, note that we have to first obtain the x momentum rate leaving. So it is not only leaving from the right wall, it is also leaving from the side walls. So we will take this and multiply by the velocity at the side wall, which is u infinity. So this is the momentum flow rate from the right wall. Now I'll write down the expression for momentum flow rate from the side wall, which is this, which is mass flow rate from the side wall multiplied by u infinity. These are the momentum flow rates which are leaving, x momentum flow rate. Now the x momentum flow rate which is entering is this. And for the entering we have a negative sign. So we have minus of mass flow rate and on the left one multiplied by u infinity. Okay, so this minus L to plus L we can write twice of integral of 0 to L. And if you do that, you get an expression as this. And as I had mentioned, u dot n is also horizontal velocity, so you get u square dy. And then if you take for this ms u infinity, you take this, so it will be 2 rho L u infinity square minus 2 rho u infinity integral of 0 to L u dy. This is as shown here. Okay, so this is this term which I've shown. Now I'm left with this term. So it will be minus of this ml, which is expressed as, this is given here as this ml into u infinity. So this will be 2 rho L u infinity square as shown here minus 2 rho L u infinity square. Now here you can notice that these two terms are same with opposite sign. Here you have plus 2 rho L u infinity square. Here you have minus 2 rho L u infinity square. So this two term cancels down as shown here. And now you also can notice that the 2 rho is common in this equation as well as this equation. So you can take 2 rho outside, and here you have integral of both this integral. Note that there is 0 to L dy. Here you have u square. I can take u infinity inside. So, and then I can have integral which is u square minus u infinity u, and I can take u common. So integrand will be u into u minus u infinity as shown here. So integrand is now u into u minus u infinity. This is the force that is a reactive force I have mentioned. This is the reactive force acting on the control volume. But the active force that is acting on the cylinder due to this water flowing over its surface is negative of this, as I had shown in the previous problem also. So the force acting on the cylinder, which is the force in the x direction, this we also call as drag force, is negative of this force acting on the control volume. So here you have u minus u infinity. Here you have u minus u infinity. So if you take a negative sign, it will become u infinity minus u, which is as shown here. So 2 rho integral of 0 to L u infinity minus u dy. Okay, so we have obtained the expression for F cylinder. We have to derive in a non-dimensional form. So basically this I have to divide by half rho u infinity squared d. So when I divide by half, this 2 will become 4. So rho will cancel down. Now I am left with u infinity squared d. So I will write this as u by u infinity. This I will write as, if you divide by u infinity, it will become 1 minus u divided by u infinity, and this y divided by d I will write it down, which is as shown here. So CD, the drag coefficient is given by the drag force divided by half rho infinity square d, and now it will become 4. Rho cancels down, and you divide by u infinity square, the integrand, and you get u by u infinity minus 1 minus u by u dy by d. Now we have a definition. This u by u infinity is we have defined as u star. So this is your u star into 1 minus u star. Now the small y by d is y star. Okay, so if you do that, this limits of the integral will also change. So because if you define capital Y is equal to small y by d, so at small y 0, capital Y is 0, and at small y L, this is L star. Okay, so this is the drag force that we have derived. So with this problem, the message that you should, or the main learning you should have is that while solving the momentum conservation equation, make sure that the mass conservation is obeyed. It may so happen that you are given velocity at certain boundaries of the control volume. You intentionally, they are not given at other boundaries, because by mass conservation you are supposed to obtain the mass flow rate such as we obtained from the side walls in this problem. Okay, don't miss this. This is one of the trickiest problem in this topic. So while applying momentum conservation, be conscious enough to make sure that the mass conservation is obeyed, even if it is not explicitly stated in a problem. Okay, for most of the momentum conservation, this is not stated. But you should be clever enough to judge and calculate the mass flow rates in certain boundaries where it is not given. Otherwise, you will miss the momentum transfer on that boundary and you can get into wrong solutions. Okay, this wake survey method is not only used in experimental studies, but it is also used commonly in computational studies to calculate the fluid dynamic forces acting over a body. Right now I have shown you the force acting in the horizontal direction, which we call it, because this force, if you stand in a river, it basically drags you along the flow direction, so we call this as drag force. There is another force which acts in the y direction, which is called as lift force. So using the wake survey method, you can also calculate the lift force, which I had not shown here. I had shown you only one of the force. So in this problem, as compared to the previous problem, note that intentionally the mass flow rate was not given on certain boundary, and the main learning, which is different from the previous problem, is you need to apply the mass conservation. Another difference for this problem as compared to the previous problem is that you are given, in the previous problem, you are always given a single value velocity at the inlet and outlet, whereas here you are given a velocity profile. Okay, and that we had used here to calculate the momentum flow rate, x momentum flow rate. After this 3 example problem, before I end, there is a 4th problem where I would like to emphasize that as I had mentioned in my video lecture, that for most of the problem in momentum conservation, you are given single value velocities at the inlet and outlet. So that way you can write the momentum conservation equation, which was originally proposed through Reynolds transport theorem as an integral equation. For our convenience, we have converted the integral form of the Reynolds transport theorem to an algebraic equation, where for a steady flow, we have written that force acting in the x direction. We had expressed it in terms of, basically we had keep it like an accounting problem, bookkeeping problem, where basically at the various inlets and outlet, we calculate the x momentum flow rate, which is a product of mass flow rate into the horizontal or u velocity. And for outlet, there is a positive sign. For the inlet, there is a negative sign. Okay, so this is the algebraic equation which for convenience I had proposed for most of the problem. Okay, so the first 2 problems that was presented here, we had used the algebraic form completely. But in the 3rd problem, which was the previous problem for the cylinder problem, in the outlet, we had a velocity profile. So we need to use an integral form of the equation, which was originally presented in the Reynolds transport theorem. Now, before I end, I don't want to, actually you should be aware of what is the consequence of this assumption. Wherever you are given a single value at the inlet or outlet, where basically you are not considering the variation over the cross section, so you are considering a one-dimensional, you are making a one-dimensional assumption. Now the consequence of this one-dimensional assumption, let me take up a problem and make you understand and appreciate that what is the consequence of that approximation, where we are assuming that at the inlet and outlets there is a one-dimensional flow. The velocity is not varying over the cross section. So this is the context of this problem. So this problem, the price which is associated is presented here in terms of momentum correction factor. Let me present this problem, then this will be clear to you what is momentum correction factor, which is expressed as beta in this problem. This is a fully developed laminar and turbulent flow or turbulent flow in a pipe. Laminar and turbulent flow and what is the developing and fully developed flow, all this I have discussed in my introductory lecture in the topic number 1. So let us suppose this is a pipe and the fluid is entering with a constant velocity. So here if you use that algebraic equations, it's perfectly fine because here the velocity is uniform. But let us suppose you are solving a problem where at the inlet velocity is uniform, so it's perfectly fine. You write as momentum flow rate into the horizontal velocity as x momentum flow rate. But whenever you have a velocity variation, let us suppose this is a fully developed velocity profile for the laminar and turbulent flow, where this color corresponds to laminar flow, pink color corresponds to laminar flow, where you have this is the laminar velocity profile, and this turbulent velocity profile, which is shown by green line, is a flatter profile. Okay, note that the if you take the integral of u dy, both in this case both are same because near to the wall, in the turbulent velocity profile, the velocity is larger, but near to the center, the maximum velocity is smaller in turbulent flow. So the maximum velocity, which is at the center line, this u max for turbulent is smaller as compared to the u max, the maximum velocity at for the laminar. More about this laminar and turbulent flow will be discussed in the lecture after the later lectures. In this problem, you are given velocity profile, which has been found experimentally that the fully developed velocity profile for a laminar flow can be mathematically expressed as u is equals to u max, where this u max is the center line velocity, 1 minus small r by capital R. This capital R is the radius of this pipe. Small r, so this is the velocity profile. Basically, you substitute any r and this is the radius of the pipe. And if you know the Vmax, you can obtain this velocity profile. This is what I have shown by this pink curve, this velocity profile. This is mathematically expressed for laminar flow by this expression. For a turbulent flow, whatever I have shown by this green curve, it is mathematically expressed as u is equals to u max 1 minus small r by capital R to the power 1 by 7. This is a much flatter velocity profile. And in this is the radius of the pipe, which I listed while drawing. And you have to determine this momentum correction factor. What is this momentum correction factor? I'll come back to this little later, just hold on. You have to obtain this beta for both laminar and turbulent. Okay, now let me introduce the momentum correction factor by presenting the momentum flow rate from Reynolds transport theorem. So this momentum flow rate, which is a product of mass flow rate and velocity. Now, if you see mass flow rate, it consists of velocity and surface area. Velocity is a vector, surface area is also a vector, so mass flow rate is a scalar. On this momentum flow rate, if you see mass flow rate, it's a product of mass flow rate and velocity. Mass flow rate is a scalar, but velocity is a vector. So this momentum flow rate is a vector quantity. And that way it is correlated with force, which is also a vector. And this momentum flow rate is expressed as integral of in the Reynolds transport theorem, it is integral of small v rho u dot n ds. Now that small v is a intensive property. So momentum is a mass into u vector. If you divide by mass, you get a u vector. So the momentum flow rate in an integral form, it is given by integral of surface integral. So in this case, the integral that we will be doing is over the cross section, which is a circular cross section of the pipe. And the elemental surface area which we will be considering is basically we will be considering a circular cross section, which will be 2 pi r dr in this case, and we will be integrating from 0 to capital R in this case. So this is the momentum flow rate in an integral form. However, for our convenience, since most of the problem you are given a single value instead of this velocity profile. This is the expression. So from the momentum flow rate, you can obtain x momentum flow rate where you take this velocity vector as a horizontal velocity, which is this. So the x momentum flow rate, it is same as this, but only this u vector now becomes the component, which is the x component, which is u, y component is v. So now in this case, the cross section which we are taking is a circular cross section, which is a vertical cross section which we are considering. And if you draw the normal, it is on the horizontal direction. The velocity is also in horizontal direction. So if you take the dot product, it's also u. So here again, it is basically a surface integral of rho u square ds. Okay. Now this is, there is an equal sign, and I will draw your attention that I am using a sign. This is called as an approximate sign. Okay, so this is an exact representation of x momentum flow rate. So integral equation is an exact representation. The algebraic representation is an approximate representation. Note that. And what is the approximate representation? Approximate representation is, let us suppose for the fluid which is leaving the pipe, fully developed flow, you are given, let us suppose, an average velocity. So let us suppose instead of this velocity profile, you are given an average velocity profile. So what we do is that since we are given a single value, we calculate the x momentum flow rate, which is the same x momentum flow rate, which we had presented earlier as integral. When you are given a single value, which is an average value, we consider that single value corresponds to the average value. And that average value, this is the velocity in the horizontal direction. If you multiply by the mass flow rate, this is the x momentum flow rate. Now this mass flow rate is given by, in terms of the, if you use an average velocity, is density into area multiplied by the average velocity. So you have, so then it becomes rho u. So if you take the product, so you have rho u average delta s, and then you multiply by u average, it becomes rho u average square delta s. So the momentum flow rate, the exact expression is this. Now we are approximating by this. Okay. Now, if you want to understand what is the price associated with this approximation, let us, instead of this approximate sign, let us use an equal sign. And as I said, this approximation is because we are using a 1D, where we are considering that u average is almost uniform. Now, if you see a turbulent velocity profile, it is uniform for a much larger height, and very near to the wall it is non-uniform. But in a laminar flow, it is not so. Okay, so this indicates that probably for turbulent flow, this assumption is better than at least for laminar flow. However, if you want to understand what is the price associated with this approximation, we will use we will equate it, but we will introduce one factor which we will call as beta, as shown here. So this beta is like we want to quantify this approximation which we are making, and this beta is called as momentum correction. So while you are writing an algebraic equation, strictly speaking, when you write an algebraic equation, each of those momentum flow rates you should multiply by beta. However, later on, if you do this exercise for laminar and turbulent, there is a message that you will get. You will learn something. I'll hold on for some time till then, and I'll come back to this towards the end of this tutorial. Okay, now let me add this. Okay. Now, basically, now I'll obtain expression for beta. To obtain the expression for beta, I will equate what is this with this. What is this? This is integral of rho u square ds. And what is this? Rho u average square ds. So if you equate this with this, rho cancels down from the left and right hand side because it's an incompressible flow. Okay. And beta will come out to be integral of rho u square divided by u average square ds. You will also get 1 by delta s, which is as shown here. Beta will be 1 by delta s integral of u small u divided by u average. You can take whole square ds. So here you have u square. This u average square, if you divide, you can write it like this. And this delta s comes in the denominator. Rho cancels down from here and here. So this is the expression for the momentum correction. So this is the first part of the solution where I have shown you the derivation of momentum correction factor, where basically I started with the exact expression for x momentum flow rate as an integral equation. Thereafter I showed you an approximate representation. I change the approximate representation to an exact representation by introducing this term beta, and that way I have derived the equation for beta. Now, if you are given this velocity profile, here u is as a function of u max. Here you are now this beta calculation wants u average to be calculated. So now in the next step, what we will do is using this velocity profile. Let us first calculate the u average. Now, how do you calculate u average? In the previous topic on mass conservation, I have mentioned for an incompressible flow, u average you obtain as 1 by surface area, which is pi r square, if r is the radius of the pipe, 1 by pi r square integral of 0 to r u ds you want to do, which will be 2 pi r dr. So u average is 1 by delta s, integral of u ds delta s. Now the surface area is pi r square, so it becomes 1 by pi r square, and this ds we take a elemental length 2 pi r dr, so which is given there, and we integrate it from 0 to r. Okay, so we note that we integrate it from 0 to r. This we integrate it from 0 to r, and this u, if you substitute it from here and integrate from 0 to r, finally you can obtain expression this u average as a function of u max by doing the integral. Okay, so from this you will obtain u average as a function of u max, and that u average you substitute here. And finally, for laminar and turbulent flow, if you do all those integrals, finally for laminar flow, you will find that beta is equal to 1.3 for fully developed flow in the pipe. And for a turbulent flow, it is 1.02. And what beta you were taking in this approximation? It is like you are taking beta is equal to 1. Okay. So, what is the price associated with it? For turbulent flow, it's like 2% variation, which you may consider negligible. So 1D approximation for turbulent flow is good. So the algebraic equations, if you use for momentum for turbulent flow, it is fine because the error is small. However, for laminar flow, note that there is a like 33% additional value which are involved. Okay. So if you want to, so if you are given a laminar flow, so if you like, even if in a flow in a nozzle or so you need to take this into account if, for a more accurate calculation. However, for most of the problem which are given for this problem, you can ignore it. But in certain problems, if you are already given a beta, then you need to consider. So with this, I had presented 4 different example problems. The first and second problem, where I had presented the first problem, I had introduced the moving control volume. In the second problem, the new thing was I had introduced the Bernoulli. The first problem was on the jet striking on a vane. So we had a stationary vane. Let me show it quickly. Quick recap. So in the first problem, we had a moving vane, and so in this we have learned how to handle the moving control volume, where we use the relative velocity not only for the there are 2 velocities which are involved in exponential flow rate, one in the mass flow rate, another the velocity outside. For both the velocities, you have used the relative velocity. So I'm highlighting the key thing for each problem. In the second problem, the key thing is that you have to use Bernoulli equation to calculate the pressure. And in the third problem, it should happen that you are given, instead of single value, velocity variations, and you have to apply mass conservation to calculate the mass flow rate on the side wall. So this was the key thing for this problem. And finally, I wanted to demonstrate that the algebraic equation that you use is an approximate representation where you made a 1D assumption. So, and the price associated with it I had shown. So for most of the problems, if it is turbulent, then your approximate representation, algebraic representation for the momentum conservation is good. However, for laminar flow, there are certain inaccuracies in your algebraic representation based predictions. With this, I had come to the end of this tutorial video. Thank you for your attention.